Hello, my name is Rothomio Jonathan. I'm going to be taking you through local search and adversarial algorithms that's in artificial intelligence. Uh, Hill climbing algorithm is a greedy algorithm that incrementally moves towards better solution. It's where like when you're climbing a hill, you're trying to reach the top by always moving upwards. Like you see a top peak, you want to try and move towards it. So in the same way, it searches like going upwards, like always going towards better solutions. And then like when it gets a better solution, it gets there. But then sometimes the better solution isn't the better best solution. So that's its drawback. It's easily trapped in the local optimum. Like it feels it's the best, yet in general it's not the best. Like when you look at this graph, there is the local optimum, then there is the global optimum. So when you arrive at a smaller peak, you may think you're at the highest peak when you're not in the highest peak. So that's one of the drawbacks of the hill climbing algorithm, and it's applied in job allocation system where you are optimizing employee assignments based on criteria such as workload balance and maybe efficiency. Now there is also the simulated annealing algorithm. Now this one expands on hill climbing by allowing worse solutions to escape local optima. So it's kind of derived from the process of metals cooling, cooling gradually, slowly. So it's more of like a reverse of hill climbing. It accepts for bad moves, like when you've climbed up a hill, you may feel it's your best position when it's not. So you can actually climb back and go and look for a better solution, which might be now like the best solution, the global optimum. So it allows you to change, like to analyze and get a better solution. So it's used in urban planning, simulated annealing, and optimize infrastructure placement, maybe schools, exploring suboptimal solutions before finding an optimal placement to minimize travel distances. Yeah, so it gets the best possible position to place the schools in the urban planning thing. That's just a scenario, an example. Now we have also genetic algorithms, and now these ones are based on like the biological evolutionary process. Okay, like over time, the algorithm gets solutions and makes them better, improves on those solutions it has gotten. Like over time, it becomes better and better. Like it keeps growing much more wider. Yeah. So like the more it grows, the better the solutions it provides unto the user. So now in this scenario, we have organ donation matching, which is optimizing donor recipient matches based on genetic compatibility, agency, and geographical proximity. Uh, we also have to talk about responsible and explainable AI, artificial intelligence. Responsible AI ensures fairness, transparency, and ethical considerations, avoiding biases in algorithms like hill climbing or genetic algorithms. So, like, it makes sure the decision is clearly transparent and it's not harmful to the user. Yes, now for explainable AI, it makes the decisions understandable to the users. For example, like in explaining infrastructure choices in urban planning, where there's positioning of schools, positioning of churches, why it tells you why specifically, it shows a specific location for the infrastructure. So like it helps you, the user, understand its decision more clearly. Now we have adversarial search. Now this one is used when two or more agents with opposing goals interact. Now this one is interesting because there are two agents involved and they all have opposing goals, and one wants to outsmart the other one, the other also wants to outsmart the friend. Now here the goal of this search is to maximize one's gain like maximize one's gain without minimizing the competitor's gains. So one of its example is in business negotiations where you may be all trying to get the best outcome for you. The seller wants to get more money for you, want less money. So like we arguing it. And then also in network securities where there is an attacker and the defender like are competing in breach prevention, like each and everyone wants to outsmart the other. Yeah. Then you also have minimax and expecting minimax. Um, these minimax algorithms are used in zero sum games to maximize the current player's advantage while minimizing the opponent's. Like it ensures that, okay, first of all, it assumes that both of the players play optimally, and then each move is like for them is evaluated by the best outcome for the current player and the worst possible outcome for the opponent. So like it predicts the current player's moves and the best possible outcomes of the opponent. And then it's like analyzes and sees and aims to maximize the current player's advantage while minimizing the opponent's possible gains. So that's especially in chess. And then we also have expecting minimax. This one extends the minimax to include chance events in decision making. Then you also have alpha beta pruning algorithm. This enhances minimax by cutting off branches of the decision tree that don't influence the outcome. So its specific purpose is to increase search speed and efficiency without affecting accuracy. So it inverts, like it cuts off branches of the tree that won't influence the final decision, like where it's already clear that the outcome will be eh, worse than the previously considered branches, so it cuts them off. Now, it's more specifically applied in tic-tac-toe, where there is skipping moves that lead to certain losses and stuff. So you only allow moves that lead to your goal, your purpose. Then lastly, we talk about adversarial machine learning. This one is where attackers or hackers manipulate input data to trick machine learning models, like changing just small details to make the machine think it's the right one, or maybe to make it misidentify something. Like for an example would be perturbations in facial recognition causing misidentification. So like changing few pixels in an image might make like the facial recognition system to misidentify a person. Maybe you want to log in into a system using a person's facial identity. So its relation to adversarial search is that they both involve competing entities trying to outsmart each other. So that's all about it. Uh, Thank you.